fourth Maxwell equation. And in this case, we start from a current, okay? Let's say that we have a wire. And if you have a wire, it will generate a magnetic field, okay?
Well, if you have a wire with current flowing through it.
Yeah, so,
yeah.
Of course. If you have a wire and you have a current through the wire, if you have the current itself, it doesn't generate anything. Let's say that we have a circumference with a radius r. And what happens? Once more, we have a field, in this case, a magnetic field. I would like to call it H now, rather than B. And probably you will see, so this is magnetic flux density. Let's write it down. Magnetic flux density. And this specifically is magnetic field, okay? So this magnetic field will be, again, tangential in all points. Okay. So once more, we calculate the line integral over this line L of the magnetic field H dot dl, and for dl, let me find another color. dl, again, you have, like it happened before, the dl in this case is always parallel to h. So if you make the integral of h dl or b dl, well, doesn't matter. Okay, we can simply say that b is equal to, in this case, because we are in air.
Is that a free space?
We are free space, so mu 0, b is equal to mu 0.
Okay, so it's just a constant.
So we can say the integral of b, fine. So we can say that here we have our b. And it's equal to what?
Okay, well,
so here, don't forget that.
Yeah, it's a line integral.
It's closed.
Firstly, the current flowing through it, through the surface.
So it's what?
So there's an I enclosed in the surface. And then there's the magnetic permeability, mu.
In this case, mu 0. Which is how much?
4 pi 10 to the minus 7.
Unit?
I don't know.
Henry per meter.
Henry per meter.
Then maybe we find out why it's like that. Okay. Why I was saying this, I was focusing on this difference. Because if you divide by mu on both sides, what happens?
Well, the mu disappears.
Okay.
And it comes over to the side.
So here you have the current. Okay. But you know that B equal mu 0 H. So here you will have, okay, let's make all the steps because you need to make all the steps, correct? So 1 over mu 0. The line integral of B is mu 0 H, okay? Over the line L, okay?
Yes.
So this disappears, and you have the integral of H dl over the line L equal to the current. Now, if I ask you which is the unit of measurement of H, what do you think it is?
It's Weber.
H.
Yeah, because B is Weber per meter and H is Weber.
B is Weber per meter square, Tesla. Flux density.
Excuse me, yeah, Weber.
Yeah, but don't think about that. Look at what happens now.
Well, now you could say that
Let's say that
it's ampere over meter.
Ampere, exactly.
Meter over meter, yeah.
Why? Because here you have an H, which is in amperes divided meter.
Oh.
And I integrate it over the L, which is a meter. Okay? And that gives you what? The current inside.
Yeah, just A.
Ampere. So what you're doing is, for instance, let's say that you have a circumference, R. And this means that all the points are at the same distance from the center. So H will be the same in all these points.
Yes.
Or the amplitude of H will be the same, and the direction will be radial, will be tangential in any point like this. What is the amplitude? How can we find out the amplitude of the magnetic field here? Well, let's use this law. If it's constant, if the amplitude is constant, we can take it out of the integral, okay? So, because we have H, dl, they are parallel. So the cosine is always 1.
The amplitude will be proportional to the distance from the current.
Not proportional.
Inversely proportional.
So let's see what happens here. Here we have an H, which has always the same direction of the L. Yeah. So when you calculate H dot dl, they are always parallel. Here. They're always parallel because they are both tangent to the circumference always. So this will be the product will always have the amplitude of H. So you will have H dl over the line. So you have the amplitude, the integral of H dot dl over the whole line will be the integral of a constant which can be brought out. Okay? Because it's a constant, it's always the same. We are the same distance. And we can bring it out. So here we have the line integral of dl. But what is this?
That's
the circumference.
So it's going to be 2 pi r.
H times 2 pi r. And this is equal to what?
I.
Okay? So H at the end will be I divided by
2 pi
r. So if you plot it, drop down as you get further from, as you get distant from the current, okay? Fine. Here you see that you have amperes per meter, correct?
Yeah.
Because you have current over the radius. The radius is measured in meters, so you have amperes per meter. And that's the reason why it's, in my opinion, of course, the equation itself is totally equivalent, but in my opinion, it's better to show the equation with H.
Yeah.
Because then you see that the integral of H dl over the closed line L is equal to the current inside. It's straightforward. Then you saw the current, amperes per meter, you integrate in amperes per meter over meters, and you get amperes, which is the current. Okay? But for some reasons, I don't know why, but probably because in the previous equation you have B, so they want to get B as well. But okay, fine.
Well, yeah, they just put
It's the same thing.
side.
At the end of the day, you multiply mu0 everywhere. Mu0 here, you get mu0 I and mu0 H, which is B. Fine. Again, let's see what happens if you put different currents inside. So let's say that you have a wire which brings 1 amperes. Another wire which brings negative 2 amperes, and so on. So, in fact, it's not, or, yes, here you wrote enclosed, so you have to count all the currents which goes inside the ring, okay? So, a better way to write this current is to, again, try to put an integral. So let's say that in each point, there is a current density. How do you call the current density, J?
Yeah.
Okay.
This is cancelled out because of this.
Let's just keep the mu0 because, like, let's stay with the mu0. So if you have on this surface so this is a surface covered by we will get there later. Not yet. You are too fast. I want you to describe this I as the integral of the current density over the surface. Okay? Let's say that here you have a surface and there is some current. And in each point there is a current density of some amperes per meter square. J. J tells you how dense is the current per unit of surface, okay? Let's say this is a unit of surface. This is J, which is in amperes per meter squared. Mm-hmm. So if I want the total current over the surface crossing the surface S, you have to make the integral of okay.
That will give you...
Show it to the camera. So you have the total current is the integral of the current density, so how much ampere, how much current you have per square meters over the surface, okay? So amperes per meter, you integrate it over a surface, so amperes per meter squared over a surface, which is meter squared, you get amperes, okay? So let's write it here. mu0 integral over the surface S, the surface which has as an edge the line L. Okay.
Why is it a line? Isn't that line?
Sorry, my mistake. My mistake. This is why it's useful to have lectures, not only the teacher, but also somebody else, because he will find out your mistake.
Yeah.
Of what? The current density crossing this surface.
Yeah, orthogonal to the surface.
Exactly. The S. Okay. And that works fine. It gives you the opportunity to calculate the magnetic field. But of course you were saying that something else is missing, okay? And you were trying to write it down, this equation, by remembering the equation. I want to arrive there using another
by logic
approach, okay? Let's describe a typical situation, okay? Let's say that we have a common circuit. You have a battery, you have a switch, you have a resistor, you have a capacitor, okay? Here you have some voltage, let's call it V1. And let's say this capacitor is not charged. Okay, so the charge here is 0. Wait. Don't run. So if the charge is 0, the voltage is
0.
0, okay. Because we know that Q equals CV, so the voltage is equal to Q divided by capacity. So if there is no capacity, here, there is no electric field, there is no charge, and if there is no electric field, there is not voltage, because the voltage is the integral of the electric field over a path. Okay? If there is no electric field here, you go from here with your charge, you bring it here, and there is no
potential.
There is no energy going inside or going outside, because there is no charge, so there is no force. If there is no charge on the edge, on the plates of this capacitor, there is no force preventing you to move the charge on one direction or the other. So there is no electric field, therefore there is no voltage. Fine. Now, what happens if you close this switch?
The
So first of all,
capacitor
before
will
you
start
switch,
to charge.
let's say that you close it at t equals 0. The current is clearly
0.
0. The voltage here, we said the voltage on the capacitor is 0. What happens when you close it?
Capacitor will charge up.
Okay. And the current? So this is what?
This is voltage.
This voltage, and it arrives to?
V1.
Okay. And the current? Let's do it on another axis, because I want to show exactly. So this is the current, and it starts from?
It starts from infinity.
No. Be careful. Look at this circuit. When you close it, the very same time that you close it, what happens?
Current starts flowing.
Yes, but here the voltage is still 0, because not a single electron arrived to this capacitor, okay?
So theoretically, the resistance there is
Not
0.
theoretically, let's say practically.
The resistance is 0.
No, the resistance is, I don't know, 100 ohms.
Yeah, but at the capacitor, it's 0. Because...
It's a capacitor.
Yeah.
It's an ideal capacitor. There's no resistance.
Okay, but
Wait. So here you have three voltages. VR, V1, and VC, okay?
Yes.
So you have V1, VR, and VC. Now, VC is 0. So VR is equal to V1. Okay. So if this voltage is 0, it means that this point is at the same potential of this.
Yes. So the current will be V over R.
V1 over R.
Yeah.
Okay. So when you close the circuit, if this capacitor is discharged, there is 0 voltage between these 2 points. So all the voltage must be here, because there is this voltage is 0. So if you make the calculation, in this case, Kirchhoff law at the voltage applies. There is no magnetic field which crosses the board. So you close this voltage is 0, the only 2 remaining voltages are this. So the voltage on the resistance is the same voltage of V1, so the current will be starting from V1 divided by R. Then what happens? The current changes, so the charges arrived here, they develop some charge. As they develop some charge, this voltage increases, because the voltage is proportional to the charge. So you pump the current, you increase the more current arrives there.
The more charge there is.
The more charge arrives there, until
The capacitor is full.
the capacity will have the same voltage of the source. At that point, VR will be 0, because you will have V1, which is equal to VC, when this VC will reach, sorry.
V1?
V1 is equal to VC if you charge it large enough. So if you have this voltage equal to this voltage, there will be nothing left here.
Yes.
And at that point, there is no current anymore. So when you give current for long enough time to charge the capacitor to the same level of V1, then current cannot flow anymore because there is equilibrium. V1 equal to VC, so where does the current should go if it's in equilibrium, if it has the same voltage? Okay. Fine. So here the current changes. And we have this situation where you have basically a capacitor let's say that we have a capacitor. I will just draw it without the whole circuit, with some current, a current which has this behavior, okay? It starts from here and it drops down. Now here, you said it doesn't...
It doesn't really go to 0.
Yes, but okay, we can approximate that if you wait for infinity, it will go to 0.
Okay.
So this is the current, this is the time. Okay. Let's keep this situation, okay? And let's work with this. I don't draw all the circuit.
Okay.
Let's work with this capacitor. And, well, actually, I will draw it more here. So, remember, if the laws apply... one thing I didn't mention is that this law applies again for every surface, okay? When I said, this is an important thing I forgot. We said, okay, we have our loop. We have some current going through the line. And we said that the total current which crosses this surface is equal to the integral of the magnetic field over the circumference, okay? Yes. I said that, I forgot to mention that this applies for every surface. So not only if you have like this a ring and this surface, but also if the surface is like a bag, like that. As long as the edge of the surface is attached to the ring, okay? So why? Because if the current enters here, there is not a black hole which takes the current away to the magic word, okay? So if the current enters here, whatever is the surface, if it enters here somewhere, it has to go out, okay? So it doesn't matter where actually, it's not really precise. You will see later why. Well, okay, I don't want to be too formal. The point is, okay, so this applies to each sort of surface. So the surface does not necessarily need to be attached flat to the surface, to the ring, but it could be, I don't know, our bag like this. Connected there.
Yeah, okay, yes.
It applies to any surface, okay? As long as it is attached to the edge of the line L, okay? So this is S, okay. Fine. Now, let's watch this capacitor. What happens? You have a current there, right? Let's say that instead of having this random current, we have the current which goes to the capacitor.
Okay.
Okay? Still a current. We don't discriminate. It's not a different current. We love that current as well. Each current is beautiful. So, let's say that this is our capacitor. And there is a current. Current generates magnetic field. Okay, so I can say that I take a circumference like this, and the circumference has a radius r. Okay. So we are here, here, and the magnetic field will be tangential. It's the very same thing that now I'm making it horizontal when before it was.
Yep.
Okay. That doesn't change. Okay. So we know that if you make the integral of B over this line L, you get the current which crosses this surface, okay? Which is this current I. And the current I, we know it has this behavior over time, okay? Fine. I have a magnetic field here. And it's generated by this current. So you take this plot, you consider the geometry, you know that H is equal to the current divided 2 pi r, and therefore B is equal to mu0 H. So it's mu0 I 2 pi r. Okay. So this is just the same at a given distance r.
Yes.
Is the same.
Same shape.
So you know there's a current A, and the current generates this magnetic field. We are happy. Now the question is, what happens if instead of choosing this shape here, sorry, this surface, okay, I will choose another surface which is slightly different. Let's say, let me find the green chalk, that I have a bag which covers one of the plates of the capacitor. Okay, just imagine that.
Yeah, I see it.
This is your ring, and I don't know, I don't have anything like here to simulate a capacitor. Maybe my wallet. So I said that my wallet is one of the plates of the capacitor, and it will be inside here, okay? So the current arrives, goes through the ring, and it arrives to only one of the sides of the capacitor, okay? Now, I'm asking you, how much is the current which crosses the surface? The current enters here, right? But it never leaves the bag. The charges arrive there, and they are stored on the capacitor. Correct?
Yeah.
Mm-hmm. So, confused?
Well,
do you see it first of all?
Well, I was seeing that the current would flow and then generate an electric field.
Exactly, but you see that the current doesn't go there, doesn't cross the surface.
Yeah, the current doesn't cross the surface, but the electric field does.
Exactly. Wait, so the current arrives there and doesn't go anywhere. The charge arrives here and stays on the plate of the capacitor. So definitely, in this case, this equation doesn't hold anymore, because we chose a specific surface, a bag, which keeps...
Oh, okay.
So there should be something else, because the magnetic field is there, okay?
Yeah,
if the magnetic field is there, but there is no current, there must be something else.
Yeah.
Because this contribution is 0 because there is no current crossing this bag.
Yes, yes.
If the bag includes the one phase of the capacitor. But this is not 0, it's still the same. Right? If there is some current here, I know that there is a magnetic field because there is some current.
Yes.
So that's why this is in fact the only actual contribution of Maxwell.
Is it?
Because we call it Maxwell equation, but Maxwell just did only this tiny part. Everything else was done by other kids. So this was Ampere's law. Ampere tells you, okay, you have a current, you have a magnetic field, and the magnetic field is given by the amount of current which crosses the surface. But then arrives Maxwell and tells you, okay, what if I take this surface? I still have the magnetic field, but I have no current crossing the surface. So, Maxwell is telling you,
okay,
there is some other contribution which compensates for the fact that you don't have current anymore, and is given by the electric field.
Yeah, because the current gets converted to electric field, doesn't it? Well, not converted, but the current generates the electric field.
Yeah, the current is some charge which arrives to the capacitor, and if it changes, so...
Well, if the current changes, the electric field will change. Well, also the magnetic field.
Mm-hmm. So, let's calculate the flux. Okay, again, the electric flux.
The electric flux. Oh,
over the surface.
It's the same as the magnetic flux. We
So?
just get we get a derivative.
No.
Oh, sorry. We just get the surface integral of the electric field with respect to that surface.
Okay, so again, you have in any point here an orthogonal vector ds.
Oh, don't worry.
And again, we're calculating how much flux goes through the surface.
Yeah.
Okay. So it should be perpendicular, blah, blah, all these sort of chats. So this is the flux. But it's not enough to have a flux. It should change in time.
Yes.
Why? So I have mu0, epsilon 0. So mu0, you can take it then as 1.
Yeah, because of h.
Then you have the derivative over time
Yes.
of the electric flux. So is the integral of E ds over
Surface.
the surface. Okay, this is open surface. So again, let's draw again. Here you have the current. Here you have your capacitor. Now, this current will generate
A field.
an electric field inside the capacitor. Therefore, when I take, let's say that I have here this circumference, and I take this bag, which includes one phase of the capacitor, here I will have a flux, okay? Because here I will have an electric field because I am inside the capacitor. So now I have a flux, and this flux changes in time. Okay? Why? Because I start from a situation, from this condition where I have 0. So here I have 0 charge, so the electric field is 0. Then I pump some current, I build up the charge, so here it will be build up the charge, so I have an electric field, until it doesn't change anymore because I arrive to
Equilibrium.
So the voltage of the capacitor is equal to the voltage of the generator, then the charge doesn't change anymore, and the electric field is 0, okay? So this electric field changes in time, and it gives rise to the magnetic field. So if you take the surface before the phase of the capacitor, you have 0 electric flux because you don't go inside the capacitor where you have the electric field. But you have the current. Okay, so in the first situation, the first condition, let's draw both conditions, both cases. Okay, so let's call them case A and case B. In this case, you have the current. So you have the magnetic field generated
by flowing current.
By the current, okay? So this gives the magnetic field in case A. In case I select the surface B, the current becomes 0 because it doesn't cross the bag.
So
but I get...
Well, no, the current's not flowing because the capacitor is charged.
No. Even if the capacitor is not charged yet, it's still charging.
Okay, it's still charging.
So let's say that the current, we are here.
Okay.
So the current is pumping up. So the electric field is changing. It's changing because the current is still
charging the capacitor.
Okay. So, so in both cases, here the current is non-zero. It's flowing current, magnetic field, and we are relaxed about that. We know that if you send a current in a wire, you generate a magnetic field. Okay. If I'm still here, same condition, the current is the same, but I choose another surface, then I have current 0 here, because the current arrives here, but it doesn't cross the surface. But I have a flux of electric field that I didn't have before, because here I didn't have electric field. It doesn't go inside where there is electric field. Electric field is inside the capacitor, okay? Because here you have the charges. So here you have the electric field. Here no. So here you have 0 flux of electric field, but you have current. Here you have no current, because you chose in this way the bag, the surface, but you have a flux. Okay. What happens when you arrive, ideally, to 0 current?
Oh, well, the B field will be 0.
The magnetic field will be 0 because here you don't have current anymore.
Yeah.
So 0 current, 0 magnetic field. Here you have an electric field. Yeah. Because the current doesn't flow anymore. But it doesn't flow because the capacitor is full.
Charged.
It's charged.
So it's 0 now because there's no flow.
No, there is a flux of electric field.
Okay.
But it doesn't change with time.
Okay, that's what the derivative is for.
Exactly. That's why here we have a derivative, okay? Here, when I charge up my capacitor, so I will be there.
Okay, so the derivative is sort of like an if condition. If it's moving, then only count the electric flux.
Yes. So let's say that here I have my V1. Here I have my capacitor. I closed. I pump up.
You pump the capacitor?
I charge up the capacitor. And therefore here I get some voltage.
Yes.
So here I have the electric field. Because here I have a voltage, so I have a charge. You remember?
Yeah.
So if I have a voltage, I have a charge. If I have a charge, plus, 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 minus, 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 I have an electric field. So here I have the electric field after the current arrives to 0. Doesn't mean that I have 0 voltage.
No.
It means that it's charged and therefore there is no space for putting extra current, okay? So I have an electric field, but because it's already full, the capacitor, you cannot...
it's not changing.
It's not changing. And if it's not changing, the derivative is zero, okay?
And then,
which fields, because if there is no current anymore flowing, there is no magnetic field, okay? So this applies only in this case if you get this surface. But if you want a universal law, which applies always for each surface, no matter how you choose it, then you have to add this one, because this is called displacement current, something like that.
Yeah, yeah.
Okay.
And that's sort of like, let's say, the unknown with electromagnetic fields in space. From what I recall,
the unknown depends on...
Like when it's in space, there's a displacement current or displacement field, but there's nothing actually there that's being displaced.
What do you mean?
Okay, well, it's probably a rough memory, but from electromagnetic field theory, the professor was explaining to us the displacement current that's generating the EM field or the EM wave, and then he's like, but don't ask me what this displacement current is, because I don't know. Because in space, there's nothing there, so what is being displaced? That's the point.
This could be a little bit misleading, because displacement current makes thinking that you change...
Something's moving.
It's moving.
And in a way it is, because the current's moving, which is
Yeah, but let's give another name if this is confusing you. Because yes, if you say displacement current, means it makes you thinking that there's something moving, some object which is displaced.
Yes.
As a matter of fact, there's no object which moves. You can say moving time or changing in time if you think the electric flux. So, I don't know, maybe displacement current is not a good name. But again, let's not focus on the names. Let's focus rather on the concept. Okay? The concept is that you should always have something which holds with the reality.
Yeah.
Reality is that
there's some charges.
There is some current, and the current generates the magnetic field. And you have a current, even in this case. So there are some cases where the current is like 0, then going down, starting from this value, and going down. In all this portion of time, the current is non-zero, is flowing, even if then goes down to 0. But there is current, and if there is current, there is magnetic field. So it doesn't matter if after infinite time goes back to 0. Still there is current, there is magnetic field. Even if the charges are not going back to the generator, but they are charging up the capacitor. So you don't have a current which starts from here and go back, but you have a current which moves the charge to the capacitor. Okay? So it stores the energy on the capacitor. So even in that case, you have a current, and if you have a current, you have a magnetic field. But how can you justify that if at some point there is no current crossing the surface? You have to introduce this term. So either you have, let's say, real current. That's maybe not a good way to say it. Let's call this real current. Mm-hmm. So charges which move in this wire and they arrive here. Or you have the displacement current, or let's give it another name. Let's invent another name. That's, how do you feel it? Like
field current.
Field current? Okay, why not? Or yeah, this field current, which arrives here and changes the electric field, which again gives the same effect. Okay. So now this is the integral part. So is the concept clear?
Yeah, perfectly.
Okay. So this is the physical explanation of why you have this term. Okay. So again, I don't remember myself this equation. I have always to think about that. So sometimes I forget about, yeah, there's a mu zero here, whatever. But this must be the concept, okay? You take a bag, you take this specific case and say, and then there is no current crossing the bag. So, but what is changing here? What compensates for the fact that there is no current? There is an electric field created by the current. And it will create a magnetic field only if it changes, okay? So, because here you have either a current which changes, or
a field which is generated.
Sorry, either you have a current, but if you have a current, it does change. You cannot have a constant current here.
Yeah, not in that case.
Because then, if a constant current, here you have always a transient, okay? So, you have a current. If you have a current in this situation, it changes. And if it changes, it means that here you have an electric field which is changing. Therefore, you have a derivative of electric field, okay? So always try to remember, okay, what changes here if I have a current? If I have a current, is a current which changes, because you have a capacitor. And if you have a current which changes, it means that the charges are going somewhere to build up an electric field, to store charge here inside the capacitor, and therefore it creates an electric field which changes, because the current is changing, so it's pumping up charges to increase the electric field. So either you have the current, or you have the effect of the changing current, which is the changing of the electric field, and in this case, it's integral over the surface, okay? So always try to remember
the components of the equation.
What it means. So yeah. Keep in mind, this example is good because it gives you some
visualization.
Of
yeah, especially the bag. So we could express this as...
So again, you have your loop. And when do you get... So how is the field here?
This would be the curl because it's a rotating field.
Yes, okay. So it gives a net contribution if it's rotating, okay?
And that is equal to. Now we can use the current density.
Current density. So instead of having a surface, we shrink it down to the single point.
Yes.
And the single point we get...
Well, okay, so mu doesn't change.
Mu 0. So let's open a parenthesis, okay? So instead of having the integral of the current density over the surface,
we're going to have the current at that point, which will be rho over...
No, current density only.
Just current density?
Okay. Rho is the charge.
Charge density, yeah, excuse me.
J is like how many amperes per meter square you have, okay? Then you integrate it over the meter squared and you get the amperes.
Of course, yeah, and it cancels out.
So then you have only, so J. Then again, instead of having the integral over the surface, you watch only about...
It's going to be the curl of the electric field.
Oh, why the curl? This is the electric field which is... Don't forget, this is the flux over the surface, okay? So this is the flux over the surface.
So just the electric flux.
Electric flux, but in a single point is... No, this is the derivative of the flux, sorry. So this is the flux.
Oh, the derivative of the electric flux.
The electric field.
Oh.
In a single point, like, this is the surface, okay? What is the flux? If you have an electric field which crosses the surface, what is the flux? This. The flux is the integral over the surface
of the electric
S
field over the surface.
Over the surface, okay? If this is ds. Fine. But now I shrink down and I get to a single point. So I don't have a surface anymore, I have only E.
So it's just the electric field.
Yes. Okay. Fine. There is a relationship between magnetic field and electric field, but this relationship connects them only if...
The electric field is changing.
Exactly. So if the electric field changes in time, because otherwise it would be just this part where you have a constant. And again, think about the capacitor. If you have a constant current, it means that it can be only zero.
Yeah, well, the capacitor is not charged at all.
Exactly. Or it's fully
charged.
charged.
Well, it actually wouldn't be constant. It would drop over time.
Yeah, of course. They never get down to zero. Okay. So, again, only if you have an electric field which changes in time, it will generate a
rotating magnetic field.
A magnetic field. Then it will have this curl around, but it will have it's a magnetic field. And that's the same thing we saw before. Before we saw that we have a ring and the magnetic field which was going around, changing in time. It has a magnetic flux changing in time. It was generating a voltage, and therefore we have some current. If this was copper, we have some current in the ring. Okay. So we had the magnetic field B going inside, creating a magnetic flux, changing, and that was creating an electric field
within the ring.
Within the ring that gave the voltage and then the current. Here it's vice versa. We have an electric flux over the surface, like in the capacitor here. Okay, an electric flux. It generates what? Magnetic field. Okay, so it
seems like you can use this equation and the previous equation to sort of get to electromagnetic waves where they are complementary.
These four equations describes electromagnetic waves.
All four of them.
There was a very nice meme where there were the four Maxwell equations, and on the top it was written, and God said, let the light be. And there was the Maxwell equation, because that describes an electromagnetic wave, right?
Yeah.
So those four equations describe fully the electromagnetic fields in any condition. Static, then if it's static, the derivative goes to zero. And pops your uncle. If they are changing in time, then you have the terms here which fix everything, and that's everything. Like I should find some example. Okay, these are in vacuum.
Yeah, because of mu.
Then there are also the material. So, for instance, I remember when I was young, I knew that about the skin effect, right? You know what is the skin effect?
Yeah, the magnetic field pulls the current away from the center of the conductor, therefore the effective resistance of the conductor is reduced.
So if you have a conductor and you have high frequency, or generally speaking, any current which is not constant, the current is not uniform, but it will be on the edge.
Yeah.
Okay. So therefore, even if you have a conductor which is large, but the current flows in the edge, and for some times, my teacher said, okay, that's it. Trust me. And I didn't really like it. Until, I don't know, it was maybe 2004. Finally, we studied Maxwell equations, and they explained me why this happens, okay? So maybe another time we can go through that and see in more details this fact. But this is to say that once you have these four equations, you can, in fact, describes all these phenomena, because it's a whole set of equations which tells you everything of how this magnetic field, electric field, or together electromagnetic field work. Okay, that was pretty much everything for Maxwell equations.
All right.
And do you want to write them down all together, trying to remember them?
Okay.
Okay, so let's clean the board. So my suggestion is, try to write them down without remembering them, but try to repeat the concept we used to arrive to those equations.
Okay, so Gauss's law of electric fields states that the electric flux leaving a surface is
What type of surface?
a closed surface. Is equal to the amount of charge in that surface divided by the electric permittivity inside that surface.
Okay.
Okay.
Can you describe the example? Like if you have a ball with a charge inside, what does it mean?
Okay, I can.
Do you understand? Do you remember how we calculated this? Starting from the force of electric field.
Yeah, but so in a visual perspective, imagine we have a cube. Okay. And the ds is a very small area within that cube that is orthogonal to that surface. We then have, we can imagine a bunch of fields radiating out of this cube. We take the dot product of one of those vectors with the orthogonal vector to the surface, and that gives us the component, that gives us a parallel component with respect to this orthogonal vector. And that is basically the electric field, the magnitude of the electric field in that direction. Okay. So I'll actually take this one and this one.
But may I ask why you chose a cube?
It's easier to show, but I learned it this way. It's how I was recalling it in my mind. Okay, and then we just imagine that this is really small. We have our dl vector, and that is orthogonal with that.
Yes.
Pardon me, ds vector. So that is ds. And then we have the electric field now, which we can describe as E parallel. Because when you take a dot product, it gets rid of the orthogonal component and leaves us with the parallel contribution towards that vector. So now you can just assume that we have a new vector called E parallel.
Okay,
right?
Fair enough.
So the integral is going to take every one of these on the surface and add them together. And that says that that is equal to the amount of charge in that surface. And they could be negative...
Not in that volume.
Pardon me, in that volume.
Okay.
That's what that means. So...
the reason why I asked why you chose the cube is that if you use the sphere, maybe it's not so easy to draw a sphere as three-dimensional, but it's easier to calculate.
Because you have
E parallel, as you called it, it's all over the same. If the charge is
in the center, yes. Where here you would have to, as we did previously, a bunch of different.
Okay, so this is first law. Okay, let's go to the second one.
Okay. Gauss's law of magnetic fields. Okay. Same thing as previously. We have a closed surface S. Of a magnetic field.
Show it.
We have a closed surface S of the magnetic field strength, which we will call B, where B is actually the magnetic field flux.
Flux density.
Yeah, the magnetic field density, which is called flux.
No.
magnetic flux density.
Flux is the magnetic field times the surface.
Okay.
Oh, okay, so.
Well, it's don't worry. The magnetic field flux density with respect to the area ds is equal to 0. What does that mean? Well, that means the amount of magnetic or the amount of flux entering a surface is equal to the amount of magnetic flux entering the surface, because magnetic there's no such thing as a magnetic monopole.
Okay.
There are only magnetic dipoles.
Can you write it down also in vectorial form? Okay. So this is what?
This is the divergence of the magnetic field is 0.
Okay. And the previous one, we had the divergence of the electric field, which was? Exactly. So the density of charge in that specific point.
Yes.
Yeah, but okay. Next one, it's called what? Faraday's?
Faraday's law of induction. Okay, that's horrible.
Think about the situation again.
Oh.
Take a loop. Take a loop. Draw it. Draw. Okay. And then, what is crossing? Okay. You have a magnetic field crossing. Show it.
It's a magnetic field. Oh, sorry. It's a magnetic field crossing a surface area, and that induces an electric field in this loop. Okay. The important thing to note is that the magnetic field must be changing with respect to time in order to induce an electric field within that loop.
Okay, and now translate this information into equation.
So that means that we have a surface area of magnetic flux density B with respect to that surface area.
Correct.
Is equal to, okay, I guess we can put it here, -1 to conserve
energy.
The conservation of energy is equal to the partial derivative of the magnetic flux with respect to time through that surface. So you can also
and the flux is
you can also express that as
no wait calm, stop. Be careful. This is the flux. It cannot be equal to the.
Oh my God.
This is something else.
Oh, excuse me. The electric field within the line is equal to the magnetic flux.
The derivative of
the derivative of the magnetic flux through the surface area of that line.
Perfect.
With respect to time.
So can you write it down as an integral, this one? Yeah, you actually did it here before.
Yeah, but it's different because we need this. Then we need this.
Derivative of what?
And then we need this.
Okay. It's not closed.
Oh yeah, it's just a normal. Yeah, it's just a normal integral. It's just the area of the circle.
Oh, that circle, yeah. Fine. Can you write it down
in Maxwell's form?
In vectorial, like
derivative.
Point.
Okay. Oh, so what does this mean? This is This is the electric field flowing around the cylinder, not the cylinder, the line.
Okay.
So that means we're dealing with a curl. So that's going to be the del operator cross the electric field is equal to...
How do you call it this in English?
Del operator.
Del? Okay.
But in the video I was watching, he was calling it like the nebula or something.
Nabla.
Nabla, yeah.
I used to call it Nabla when I was...
I don't know where del came from. I could have made it up, but I call it del. And then that's just equal to, I think the same thing, yeah, just the...
That, again, remember, instead of the integral, so the derivative is there. Remember, when you go to this form, you shrink down to the point.
Just b. Just b.
Okay. Okay. Fine. And then, let's go to the last one.
Yes.
Ampere's Maxwell law. Because Ampere's is only the first part. So here we have also Maxwell, which gives the second contribution. Okay. So
okay,
here
so
is vice versa. Instead of having
draw this first.
magnetic field generating the electric field.
Okay, so firstly, this equation comes in two parts because two people sort of contributed towards this equation. Mm-hmm. So firstly, this describes the magnetic field. Hang on. It describes the magnetic field in a loop.
Mm-hmm.
So this is a line integral.
Okay.
And this is with two parts. There's the A part and the B part. Let's first draw the A part. So the A part can be a conductor with current I flowing through it. And then that generates...
Show it.
That generates the B field.
Okay.
With a distance r. Okay.
Okay.
Then there's the B part, which can be expressed by a surface area enclosing half a capacitor.
Draw always a ring before. No. Draw the edge. Where do you have the magnetic field?
Oh, yeah, you're right.
Magnetic field is always in the same position. Okay. So the magnetic field is always here. Okay?
And then...
But then you choose another surface.
Yeah, so now it's no longer about the current flowing... Okay, it is about the current flowing through the wire, but...
Chose another surface. So here you chose this surface.
Oh, yes.
And now you have to choose another surface.
So now...
Mm-hmm. Mm-hmm. So what is that?
This is an electric field E.
Mm-hmm. So you have a capacitor, you have your electric field inside the capacitor.
Yeah, and I created this electric field.
Mm-hmm.
Okay. Okay, so now let's describe A. A is pretty simple. It's mu naught multiplied by I. Because it's just the current flowing through the wire, and then you got your magnetic permeability.
Mm-hmm.
Okay, let's describe B. Okay, so
there's no I anymore crossing the surface.
Yes. So, but let's deal with our constants. So we have mu and we have epsilon naught.
Mm-hmm.
Mu for the magnetic field, epsilon naught for the electric field. Now, the important thing is we need to note that the current will only flow when the electric field is being generated or discharged. So that means
actually it's the current which generates the magnetic field.
Yeah. So the current will only flow when it's generating or removing the electric field.
Okay.
Okay, when the electric field is changing, the current will be
Exactly.
flowing.
When the electric field changes,
So that
current
means
flows.
change with respect to time is always a derivative. And now we need to get the amount of flux
Again, sure.
that is leaving the surface area.
Okay.
So that means we need an integral. And we need a surface integral. Which is closed. Well, it's not closed. It's not.
No, it's not close. Okay.
It's not closed. Of the E field
Of the electric field.
with respect to that surface.
Okay.
Okay.
Easy peasy.
So now we can just say that that's mu naught I enclosed plus mu naught epsilon naught, the derivative with respect to time of the electric field within a surface area.
Cool. Fine. So that's all.
No. Last thing, we need to describe it in differential form.
Ah, yes, you have to describe it in differential
Okay,
form.
so firstly, the magnetic field is rotating.
Okay.
Yeah, it's rotating. So that means we're going to get a curl.
So can I erase
Yeah,
this?
of course. You can get a curl of the magnetic field of B. And what's that equal to? Well, permeability will stay because it's a constant. And now we're dealing with a point. So we're not
Okay.
dealing with the area. So that means we need to know the current density
Current
at a point.
density in that point.
So that's J. Don't mix it up with the imaginary number. Plus
That's true.
epsilon naught.
But imaginary number, it's typically small case.
yeah,
say.
but yeah.
So
But
plus
plus epsilon
zero,
naught
move here, otherwise they don't.
plus epsilon naught, and now because we're dealing with a point and not an area, we're just going to take the
Just remove the integral.
just remove the integral, and it's the electric field.
Oop. I said remove the integral, but
It's still changing with respect to time.
okay. Cool.
Yeah.